Okay, 6.3 is parametric equations and motion. You're going to learn about parametric equations, parametric curves. We'll eliminate a parameter, put things into y equals x function notation. We'll do lines and line segments, and we'll simulate motion on the calculator as well. And these topics can be used in the real world, obviously, but the most obvious situation is when you were talking about motion. So let's look at an example of that real quick. Okay, so when a ball is flying through the air, we can model the height of that ball with this equation that's found in the book. I'll call it h of t. It equals the initial height plus the initial velocity times time plus 1/2 gravity times time squared. That's the relationship between vertical height, h here, and time t. So if you were to graph this, you'd get a parabola. As time goes on, the ball reaches some maximum height and then falls back down. It's a quadratic relationship, and this is the function that, or the formula that we would use to model the height of the ball in terms of time. Now, some books use different variables. I think some books use s sub 0 for height here. In physics, we use y for h, and initial velocity is v sub I. So you can use different variables to represent these things, but this is the formula. Now, gravity in this case is on Earth is negative 9.8 on the surface of the Earth. So this turns into negative 4.9, which is what you'll see written from a lot of books. If we're talking about gravity, we're talking about a falling object, projectile, then we're talking about gravity here, so we would use g there. So here's our function. I'm going to rewrite it a little bit. So I'm going to say y of t instead of h equals, and I'll put it in standard form, negative 4.9 t squared plus initial velocity times time plus the initial height, which I'll just call, I'll call h sub 0 still. All right, so now I can see that this is my y and this is my t, but I can also write an equation for x. If we're talking about distance in x, we know that distance equals rate times time. So I can just say velocity initial, but this is in the x direction now, keep in mind, so it's a different velocity than this one, times time. So what I have now is two parametric equations for x in terms of t and y in terms of t. So the key to understanding this, and those of you that have taken physics have an advantage here, is that there's two different things going on here. And you can separate the x and the y direction. They vary differently in terms of the distance, rate, and time because of the fact of a force. There's a force in the y direction that's causing an acceleration. Therefore, we have a quadratic relationship here with the vertical because we have an acceleration. We have a change in velocity. But in the x direction, we don't, if we ignore air resistance, we have whatever initial speed we give it in the x, it's going to maintain that initial speed all the way through. So these vectors that represent the velocity in the x direction will be the same. All right, now let me look at the units real quick. I used gravity as negative 9.8 meters per second squared. Now, sometimes the book will use feet, in which case gravity is negative 32 feet per second squared, in which case when I plug that in to this right here, it would have been 1/2 of that, which is negative 16. So I'll use feet here, and I'll give this initial velocity of, let's say, 20 feet per second, and I'll give it an initial height of 5 feet, just to come up with an example here. And I'll give this an initial velocity in the x of 10 feet per second. All right, so now I've got an example then of I've launched this ball at some angle, and I can figure out that angle actually with vectors if we wanted to, because we have an initial velocity in the y of 20. We have an initial velocity in the x of 10. So I could do the Pythagorean theorem here and get about 22.36. I could also find the angle, which is about 63.4 degrees. So basically, I've launched this object with an initial velocity in the x of 10 feet per second, initial velocity in the y 20 feet per second. That's an overall velocity of 22.36 at an angle of 63.4 degrees. So I've launched some object basically at an angle here. And we can then, it's helpful to have these relationships because this relationship right here gives me a relationship between vertical height and time. This relationship gives me horizontal distance in terms of time. So I can put those together with parametric equations by eliminating the parameter, and I can get an actual xy. I can get an actual path of the ball. I can do that in my calculator as well by graphing this. Okay, so we can type this in. X is 10t and y is this quadratic. The window is going to be important. I went to the window. Now time I went from -2 seconds to 10 seconds. And then my x min, I went from -5 to 20, and y went from -10 to 30, just so I could see this parabola. What's helpful about this parabola here is that now I have all these ordered pair are my horizontal distance and vertical distance. So my x's are the distance from my starting point horizontally, and y coordinates are the distance from my starting point vertically. So I can look at a table and I can see how this thing travels through space. I would want to change my table, so I'd want to go to table set, and I'd want to maybe start at 0 seconds and go by increments of 0.1 seconds so I can get a better view of what this is doing, because it's over within the first 3 seconds really. And you can see how at 0.1 seconds I'm at 1 foot in the x and about 6.84 feet high. And then as I travel on, so at 0.5 seconds, at half a second, I'm 5 feet forward in the x and 11 feet high. So parametrics can be really helpful, and this is the perfect example where they can be helpful, because you have the vertical height, which is varying with a quadratic in terms of time, and you have the horizontal distance, which is varying linear with time. And so we can put those together, and that way we can have an xy function. I could also eliminate the parameter here, which I might as well do for this real quick. Now, to eliminate the parameter, what I would do is solve one of these for t, which is the easiest one. So I'm going to do t equals x over 10, and I'm going to plug this in to these t's here. What I get is y equals -16 x over 10 squared plus 20 times x over 10 plus 5. Now I could simplify this a little bit, and I get this quadratic right here. So this is the actual quadratic where x is the horizontal and y is the vertical. So that's that's called eliminating the parameter, which is helpful as well. Now that's pretty much the whole lesson. This one example pretty much taught the whole lesson, everything you need to know, and it's probably an example that has the most makes the most sense to people, being that it's something we can visualize and something we know when we throw a ball. We know it follows a parabola, and in fact this parabola, given these conditions. So I'll do a couple more examples, but that's pretty much the whole lesson. Okay, so I'll do one more example of eliminating the parameter here. To eliminate the parameter, you just solve one of these for t. So pick whatever one you want. I usually pick the easiest one, which in this case is y. That means t equals y divided by 6 if I solve for t, and then plug this in. So that means x equals 5 minus y over 6 squared. And I've eliminated the parameter. Now, I could solve this for y if I wanted. By subtracting 5, multiplying through by a negative, and finishing this off. So this is y squared over 36. So this gives me y squared over 36 equals -x plus 5. Multiply through by 36, and you get -36x plus 180, and then square root. So if I solve it for y, I get this equation here. But I've eliminated the parameter. Either way you write it, now I have a relationship between x and y. Now it does ask you to identify the graph as well. What you should get is, this is a square root function, so plus and minus should give you a sideways parabola then. Okay, one last example then is find the parametrization of a line through these 2 points. So I'm going to graph both these points, 2, 3. One is here, and then I have -3, 6 is up here, and I want a line that goes through these 2 points. So this is the line I'm looking for. Now I'm going to draw a vector from here to here, and also a vector from here to here. This is my vector B, so to speak. I'm sorry, this is my vector A, which is 2, 3, and this is my vector B, which is -3, 6. Alright, so what I'm going to do is draw like a vector that goes from here to here, like this. And now I'm going to start writing my equations. So my x I want my x to start at 2 here for this x coordinate right there, and I want it to go this way. So this is where I'm going to write in the slope. And then we'll add on the slope piece. So the x is going back here from the x coordinate from 2 to -3, so it's going back 5. So I want to go for the next increment of t, I want to go back 5 here. And then for the y, I start off at the y coordinate. Well, I'll start off at this point here, 3, and I want to go up 3 units for every increment of time. So there's my parametric equations. We can graph this really quick. Once again, make sure you're in parametric mode and graph this. I'm going to have to get some more t's here, so I'll go from -6 to 2 pi there and see if that gets me the rest of it, and that does. Obviously, if I just have a range of an infinite range for t, then I'm going to have a line that goes on forever. But there's our line. You can look at the table and make sure that it goes through those 2 points that they gave us to start with, which was the point 2, 3, and the point 3, -6, which is down here at the bottom. So it does, and there's our parametric equation representing that line. All right, we'll try some homework problems and hopefully make some more sense of this.